In this recording, we're going to talk about a low-pass filter. We all use low-pass filters, but it's not sure everybody can really understand the low-pass filters. So I'll call this deep dive low-pass filters. Okay, what we have here is a very typical RC filters. We have a resistor R and voltage input and output, a capacitor C here. The impedance of capacitor is 1 over j omega c. Okay, so let's figure out the transfer function first. What is the V out? Okay, this is a typical, here is a typical voltage divider. So the current go through this circuitry is V in divided by R plus 1 j omega c, and the V out is the current times the impedance of the capacitors 1 over j omega c. Right? Let's move the V into this side and clean up these equations. We get V out over V in equals 1 plus j omega cr plus 1. We just multiply j omega c here, multiply j omega c here. Okay, and we know omega equal 2 pi f. So we have V out, V in equals 1 plus 1 j omega j 2 pi f cr. Okay, I just move the omega cr to this side and 1 to this side, so you have this familiar format. So this is the transfer function of low pass filters. Okay, if f naught, we assume f naught equals 1 over 1 over 2 pi cr. Okay, this is a cutoff frequency with a low pass filter, and what we got here, it's f, the transfer function, equals 1 plus 1 j f divided by f naught. Okay, so basically here f divided by f naught equals 2 pi f cr. Okay. Okay, now let's deep dive into these transfer functions. Okay, before we are doing that, and let's remind you something about complex numbers, because this is a complex number. A complex number, basically you have a format a plus bj, and in the coordinates, if you have a vector n, and the projection or the x-axis a, projection, and the y-axis b, for this a plus bj. Okay, the amplitude, also the length, this vector is square root a squared plus b squared, and the phase angle is alpha. Alpha equals arc tan b over a. Okay. Okay, now what is the amplitude of this transfer function hf? The amplitude is equals to 1 over square root 1 over f naught squared. Okay, so that's the amplitude. This is a very important equation here. Let's dive into this equation. We have three situations here. If f much smaller f naught, that means the frequency is very small compared to the cutoff frequencies. And the f over f naught will be much smaller than 1. And in this equation, this term squared is much smaller than 1. So the whole amplitude will be equal to 1. That means if a signal is coming, if our input signal like this, the output signal will be also like that. There's no attenuation. When f equals f naught, f over f naught equal to 1, okay, then we plug this 1 into here, and the transfer function will be equals 1 over square root 2. This is approximately 0.707, okay? What this really means is when the frequency is at cutoff frequency, the signal amplitude will be attenuated to about 70% of original signals. And then sometimes people, because this is the amplitude, if it's talk about in terms of power, you just square the amplitude, you go 1/2 instead of 1 over square root 2. So it's also, we call this half power point. And sometimes people also call this cutoff frequency 3 dB point. They basically all mean the same thing. So where does 3 dB come from? It's 20, we turn this into dBs, 20 log 1 over square root 2. Okay, and this is equal to 10 log 1 square root 2 squared equals 10 log 1 over 2, 10 log 2 to minus 1. So it's equals minus 10 log 2 equals roughly equals minus 3 dB. Okay, basics they all mean same. Okay, back to here, we have a third situation, and when f is much bigger f naught. That means the frequency is much higher than the cutoff frequency. And f over f naught is much bigger than 1. And in this equation, the amplitude we know, when this term is much bigger than 1, we can skip the 1, just ignore the 1. So it's f, the amplitude of the transfer function with low pass filters form to f naught over f. Okay, and that means at the cutoff over the cutoff frequency, the signal attenuates as 1 over f. Okay, let's make a plot. We used to see this f, this is hf amplitude. Remember, we normally plot this in a log scale. If you plot 1 over f in a log scale, it will be a line. It will be a straight line with a slope of -1. Okay, and here is f naught, and lower frequency, hf, the amplitude equal to 1. It's like this, and cutoff frequency is attenuate to about 0.7, so the cutoff frequency will be somewhere here, and the lower frequency, as we know, will be a -1 slope straight line. And so the whole transfer function will be something like this. Okay, well, this point probably should be much higher, but you got the point. So that's the plot we normally say, or the textbook for a first order low pass filter. Here is a passing band, and here is a forbidding band, and here is the cutoff frequency. Okay, now let's look at the phase. Phase of this transfer function. We write the transfer function here again. It's f 1 over 1 plus j f over f naught. So we need, first step, we need to make this have a plus bj format. Then the phase is arc tan b over a. How do we do that? We multiply 1 minus jf over f naught on the bottom, and also multiply 1 minus jf over f naught at the top. Okay, so this is equals hf equals to 1 minus jf f naught squared times 1 jf over f naught. Okay. So this is a common term to both this 1 and f over f naught. So we know the phase equals arc tan f over f naught, or minus arc tan 1 f over F over F naught. Now, similarly, we have three situations to discuss. The first is when F over F naught is much smaller than 1. It's very low frequency. And low frequency, now alpha is approached to 0 degrees. That means no phase change. And when the frequency is well below the cutoff frequency, when F over F naught equals 1 at cutoff frequency, we have alpha equals minus 45 degrees or minus pi over 4. So at cutoff frequency, there's a phase change about 45 degrees. Basically, the signal is delayed by 45 degrees. Okay, when F over F naught much bigger than 1, that means a higher frequency than the cutoff frequencies, and we have a phase change opposed to minus 90 degrees. Okay, so this is a phase, and combine this with the amplitude signal, amplitude information here, and we can draw the phase diagram here, and we have F, the frequency, and the phase, and we have 0 degrees, minus 45 degrees, and minus 90 degrees here. Okay, and one below the cutoff frequencies, we have a 0 phase change like this. And at the cutoff frequency, we have minus 45 degrees phase change. And above the cutoff frequency, we have 90 degrees phase change. So the phase diagrams like this. Okay. So now we have both amplitude and phase diagrams. Combine these two, they give the whole picture with first order low pass filters. We call this Bode plots. Okay, and what this really first means, at the low frequency, for example, here we have a signal. If at that frequency we have a sine wave at that frequency, if the input is like this, the output will be identical to this. So it's the same amplitude, almost no attenuation, as no phase change. Okay. If we have a signals like this here, while above the cutoff frequencies, if you still have a same sine wave input like this, the output will have two things happen to the output. The first thing is the phase will be shifted by 90 degrees, delayed by 90 degrees, start from here. And the amplitude will be much lower. The signal will be attenuated. So the output will be something like this. Okay, this is pretty much all the informations in terms of low pass filters. Hopefully this can help you to understand first order low pass filter better.